Hello, you're welcome to this lesson. In this video, we are going to learn about the first law of thermodynamics. Okay, so let's look at that. The first law of thermodynamics states that the net change in total energy of a system is equal to heat added to the system minus work done by the system. And then we can represent this mathematically as change in the energy of the system equals net heat, okay, minus the net work done by the system. Okay, that's the first law of thermodynamics. Okay, so I'll name this equation one. So let's look at what is going to happen here. So we're going to consider the first law of thermodynamics for a closed system. Okay, for a closed system. If I say a closed system, what does this mean? A closed system is a system in which we can uh, we can witness an exchange of heat, okay, but no exchange of mass. Let's look at what that means. So let's say I have a cup of tea, okay, I have a cup of tea, and then there's tea in this cup, and then I cover the cup, okay, this is the cover. I cover this cup here. So this is now a closed system. Okay, this is now a closed system. So the reason why this is a closed system is that the cup is covered. Okay, so the tea cannot pour, or we cannot pour the tea out of the cup, right? Neither can we add any external mass to what is in the cup because it is covered. Okay, so you see that there's no mass transfer in this closed system. But if the tea is hot, okay, with time, you can see that the temperature is going to reduce, right? Which means that heat has been transferred from the tea to the outside environment. So in that case, there will be heat transfer. So you see that in a closed system, there is no mass transfer, but there is a heat transfer. So that's what a closed system is. So we are going to be looking at the first law of thermodynamics for a closed system. Okay, so let's look at that. So I can write this net change in total energy as E equals internal energy, okay, plus internal kinetic energy plus internal potential energy plus internal potential energy. Okay, so let's name this equation 2. Okay, so what will happen is that I can write this as change in E, okay, equals change in U plus change in kinetic energy plus change in potential energy. Okay, so it is the equation 2 that I have to write in this form. Okay, so we know that the U here is the internal energy, and then the kinetic energy here is the internal kinetic energy, and then we have this also here to be the internal potential energy. So from here we can rewrite equation 1, right? So we can do substitution, and then we are going to have change in U plus change in kinetic energy plus change in potential energy because Q net minus W net, right? So let's name this as equation 3. Okay, let's name this as equation 3. Okay, because we did a substitution there. Okay, so let's look at what will happen here. So in a situation whereby, okay, let me write this here. We are dealing with closed system. Okay, let's not forget we are dealing with closed systems. Okay, so now let's look at what will happen. So in a situation whereby the closed system is stationary. Okay, so let's say for a stationary closed system, for 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 a stationary closed system, okay, for a stationary closed system, if you have a stationary closed system, that means that there's not going to be any motion. Okay, there's not going to be any motion, so and therefore the change in kinetic energy and then the change in potential energy will be equal to 0 because the system is stationary. Okay, so in that case you can write equation 3 as change in U equals Q net minus W net, right? Let's name this equation 4. Okay, this equation 4 here is known as the non-flow energy equation. That's the non-flow energy equation, because kinetic energy and then potential energy are equal to what? Zero. So non-flow energy equation. You might also see NFEE, okay, which represents non-flow energy equation. Okay, so now let's look at another system. Let's look at an isolated system. Okay, so for an isolated system, okay, what will happen here is that the net heat and then the net work done by the system, okay, will be equal to zero. Okay, that's for an isolated system. So in this case, we are going to have the equation for to be change in internal energy will be equal to what? Zero, because Q net and then W net are equal to what? Zero. So what will happen here is that when you look at equation 4, what you have on the right hand side will be equal to what? Zero. So that's for an isolated system. So let's take note of that. So let's consider a closed system which is undergoing a cycle. Okay, so a closed system, a closed system undergoing a cycle. So for a closed system undergoing a cycle, we consider change in internal energy to be equal to zero. Okay, so this is the same as what we had for the isolated system. Okay, so let me name this as equation 5. And then for that, so from here, for a closed system undergoing a cycle, we have the change in internal energy to be equal to what? Zero. Okay, but one thing about this is that when we start from equation 4, okay, when we start from equation 4, we are going to have change in U equals Q net minus what? W net, right? So we are considering equation 4. So what then will happen here is that for a closed system undergoing a cycle, okay, for a closed system undergoing a cycle, we have change in U to be equal to what? Zero, right? So in that case, we are going to have 0 equals what? Q net minus what? W net, right? So in that case, we are going to say that Q net is equal to W net. That's for a closed system undergoing a cycle. Please let's not confuse ourselves with this formula here and then this formula here. Okay, so for the isolated system, okay, you consider equation 4. Okay, you consider equation 4. So after considering equation 4, we have Q net and then W net to be equal to 0. That's how come we have this equation here. Okay, so what I'll do is that I will name this as equation 4.1. Okay, let's name this as 4.1 so I will not confuse ourselves. So that's for an isolated system. And then for a closed system undergoing a cycle, that one too, you have the change in U to be equal to what? Zero. So for that one too, you consider equation 4, just that you will have the left hand side to be equal to 0. Therefore, we will have this equation here, which I name as what? Equation 6. So these are the various formulas that you are going to need in this video to solve some questions. So with this understanding, let's go ahead and try the first question. Okay, so before we try this question, I want us to talk about sign conventions. Okay, let's talk about sign conventions. So in thermodynamics, if you have heat, okay, heat entering the system, okay, heat entering the system, you consider it to be positive. Okay, so let's take note of this. Heat in is considered to be positive, and then heat out is considered to be negative. Okay, and then similarly work in is considered to be negative. Okay, and then work out is considered to be positive. And then for the last one, mass mass in is considered to be positive. Okay, mass in is considered to be positive, and then mass out mass out is considered to be negative. So let's take note of these sign conventions here. Okay, so now you are going to solve this question I have on the screen here, which says that during a complete cycle of operations, a system is subjected to the following heat transfer: 800 kilojoules supplied and then 550 kilojoules rejected. At 2 points, work is done by the system to the extent of 96 kilonewton meter and 20 kilonewton meter. And then at a third point, there is a further work transfer. Determine its amount and state whether it is done by or on the system. Okay, so that's what we are looking at now. So let's look at how we are going to solve this question here. So the first thing we have to consider is that we are dealing with a complete cycle operation. Okay, so the question says that during a complete cycle operation. So what does that mean? So let's write down the formula for a complete cycle operation. So we know that the non-flow energy equation is equal to, we have change in internal energy, okay, because Q net minus W net. Let me write this again, minus W net, okay. But for a complete cycle operation, okay, you know that what change in internal energy will be equal to what? Zero, right? Let's look at what I'm using now. So this is what I'm using now. We are using a closed system undergoing a cycle. We know that what changing Joule equal to what? Zero, right? So we're going to have Q net equals to W net. So that's the equation I'm using, because the question says that a complete cycle. Okay, so that's the closed system undergoing a cycle. So that's the equation you are going to use. So you are going to have changing changing U to be equal to what? Zero, right? So this equation now becomes Q net equals W net, right? So this is what you have now. So now let's apply this and then solve this question here. So let's write down the given data. The question says that during a complete cycle of operation, a system is subjected to the following heat transfer. So we have 800 kilojoules heat supplied, right? So heat supplied means that's heat heat input into the system. Okay, that's heat supplied into the system. So we will have heat in. So you are going to have Q in, okay, and then that's what positive, right? So we have Q in to be 800 kilojoules. That's what heat supplied to the system. Then we have heat rejected, which is the heat that was rejected by the system. So that's what heat output. Okay, so that heat out. So that would be 550 kilojoules. And then we have at 2 points, work is done by the system, right? Work is done by the system to the extent of what? 96 kilonewton meter and then 20 kilonewton meter. So one thing you have to know here is that this newton meter here is the same as joule. Okay, so we can write this as what? Joule. So we have work done by the system. Okay, work done by the system is work output. Okay, work done by the system is what? Work output. And you know work output is what? Positive, right? So we're going to have the first work output. Okay, work output. We have two work outputs. Okay, so one is what? 96 kilonewton meter, right? Which is the same as what? Kilojoule. So that was 96 kilojoule, and then one is also 20 kilojoule. So those are the work outputs. So now what we need here is Q net and then W net, which is the net heat and then net work. So we are going to have the net heat, okay, to be equal to the sum of these two heats, right? So let's sum the two up. Okay, so in adding the two, okay, we're going to have heat in is what? Positive. Okay, so we're going to have 800 plus heat out. Heat out is what? Negative. So that was minus 550. Okay, so let's add this and then see what we're going to get. We're going to have 800 minus 550, then that gives us plus 200 and what? 50 kilojoule. Okay, so that's the net heat transfer. Okay, so now let's look at the net work. So we are going to have W net. Okay, to be equal to the sum of this work output. Okay, so let's look at that. So that's going to be 96 plus what 20, because they are all positive, right? So let's look at the answer for that. So 96 plus 20 will give us 116 kilojoule. Okay, this is what we have now. Okay, so from here we are going to find the third point. Okay, we are going to find the third or the further work transfer, which we don't know. So there's going to be another work transfer in the system which you don't know. So we are going to add that to this here, which was W. It is also a work done by the system. Okay, it is also what a work done by the system. So it will also be what positive. So at the end we are going to have the net work to be what 116 kilojoule plus W. Okay, I think I have to remove this kilojoule from here. Okay, so plus W, then I can bring bracket and then bring the kilojoule here. Okay, so this is the network. So now from this equation that we have here, we can equate the net heat to what the network, right? So we are going to have 250 equals 116 plus W, right? So we are going to have 250. We're going to have 250 minus what 116, and then that should be equal to what W. So let's look at that. So 250 minus 116 will give us 134 kilojoules. So that was 134 kilojoules. So that will be equal to W. So then we are going to have the third work transfer, okay, or the further work transfer to what 134 134 kilojoule. So that's what this question asked us to do. So that's all for this video. But I'm going to solve more questions under this. So please make sure you like and subscribe.